Okay, so today we will be talking about two-dimensional kinematics. In today's lecture, we will be looking how to calculate the displacement, velocity, acceleration, keeping in mind that displacement, velocity, and acceleration are vectors. They're not scalars. We'll be looking at solving examples, and then we will be introducing the projectile motion. So the material for today's lecture are taken from section 4.1 to 4.3. In next lecture, we will be solving more examples. So I encourage you to have a look at those examples in preparation for Monday's lecture. So let's go back and visit the vector and ask you this question. The vector A here that you can see in the third quadrant is shown below to have an angle of theta relative to the minus y axis. What is the magnitude of the length of the dotted line shown? Do you know? Which answer do you think is the correct answer to this question? A, B, C, D, or E?
B.
Is it B?
B.
B. Why B?
B.
Why B?
It's B because theta is not the angle within the triangle, but it's outside of the triangle.
Well, you were tricked easily. So this one is indeed this one, which means the theta is between the adjacent and the hypotenuse, right? Which means that this is indeed a cosine theta.
Wait, could you re-explain why it's A again, please?
Remember what did we say about how to calculate the adjacent? If you have a length here in this right triangle, then if the theta is between the hypotenuse and this length, then this length is the hypotenuse times the cosine theta. So we're always looking at the cosine, the angle between the length of interest and the hypotenuse here. Okay.
Yes, that makes sense. Thank you.
You're welcome. Okay, so next question is, based on the coordinate system shown, which of the following correctly describes the signs of the components of vector B? Is it A, B, C, or D?
Is it A?
It's D.
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 Is it B?
Well, let's look at the y component. Do you see the y component negative or positive?
Positive.
Do you see the x component negative or positive?
Negative.
So the answer is D. Okay. Now let's move to the displacement and how to calculate displacement and velocity and acceleration. The definition is the same, exactly the same definition that we have seen earlier. We said that displacement is a vector starting from the initial, ending at the final destination, and we're going to call this one delta R. Average velocity is the same, the displacement divided by the total amount of time. Average acceleration is also the same, which is the change in the the velocity divided by the total amount of time. Keep in mind, in those vectors, you will see X and Y components, as we will explain shortly. So if I am to here show you what do I mean by the delta R here, if this is my coordinate, and I have position a motion happening between position A and position B. In this case, I can represent this position with the vector RA, and this position with the vector RB, right? So in this case, the delta R, which is the displacement between position A and position B, is represented by this vector, starting from the initial, ending at the destination. This is delta R as a vector. So how do I calculate this delta R? In order to calculate this delta R, which based on my understanding of the displacement, that this delta R is indeed RB minus RA. This is how we define the change in the displacement. So if I am to calculate the displacement between A and B, I should be taking the vector RB minus the vector RA. But we have seen in last lecture that in order to add or subtract vectors mathematically, we have to deal with their projections. What does this mean? This means that I have to project this RA on the X and get RAX, and also this RA projected on the Y and get RAY. Same thing for vector B. I project it on the X and I get its RBX, and I project it on the Y and get its RBY. So for me, in order to calculate the difference between RB and RA, I apply this mathematical operation on its projections. What does this mean? I can say that RB here is made of the RBX, RBY. Those are the projections, right? Those are the projections on the X and Y. And at the same time, RA is given as RAX, RAY. So every vector is represented by its projections, its X and its Y. So if I am to find delta R, I would be applying this mathematical operation on its projection. What does this mean? This means delta R for me indeed is the X of RB minus the X of RA, comma, the Y of RB minus the Y of RA. So this one is RB X minus RAX. So this is the X component. RBY minus RAY. And this is the Y component. Now I got my vector that has its own projection on the X, which is the difference between the two projections on the X. And I have its projection on the Y, that is the difference between the projections of the Y for both vectors. So in other words, if I am to look at this X and Y, which I will be calling delta RX and delta ry, then those delta rx and delta ry are the following. This projection on here, I will shift it a bit so to distinguish is this. So this one is r delta rx, and the other one I'll make it in green. Notice the direction for the delta ry. Right? So this is now my displacement. Very simple. You have two vectors. You want to calculate the subtraction or the addition. You project those vectors and you apply this mathematical operation on their projections. Now back to here. So now we know what is this delta r and how to calculate this delta r. By the way, we introduced that in the vector lecture, so I really encourage you to go back to the vector lecture, watch it again, and then watch the 2D kinematics lecture one more time. Yes, go ahead.
Sir, my question is, how are we going to recombine? Do we need to recombine the x and y values or no for the total displacement? Or can we list it as coordinates?
We will calculate the magnitude of that, and then we will calculate the direction. I'll show you how to do it.
Okay, thank you.
So you're welcome. So right now, we managed to find the coordinates for this net vector that we will find its magnitude and find its direction as we will see in this coming example. So in this example, we have a squirrel starts at the base of a flagpole that is 3 meters east of the house and 5 meters north of the fence. So this is basically the coordinates here. This dedicated squirrel completes a complicated obstacle course in 49 seconds. So the total time is 49 seconds, covering a twisted path of 18 meters. So the total path is 18 meters. The squirrel ends up at the bird feeder that is 4 meters east of the house and 2 meters north of the fence. We need to calculate the displacement, average speed, and average velocity. So let's see how to do this. The first thing you need to do is put your coordinate systems. That defines the grid we have seen for the positions of the squirrel. So here, the first thing to do is draw the coordinates. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the first point, the starting point was 3 and 5. Maybe this is not very straight. We'll do a better one. Okay, so 3. This is point, I would call it A, my starting point. So this is Y, this is X. And my second point was 4 east and 2, 4 east and 2 north. So this is the second one. So we have here the first vector. So this is similar to what we have done. And I intentionally did it this way, so what I'm doing right now doesn't look strange. So you've seen that. So we have here RA, this is the first vector, RB, and then we have the displacement between A and B this way. So this one is delta R. That's my vector, the displacement vector that I am interested to calculate. Okay, so what is RA?
4 and 2. Oh, sorry, 3 and 5.
3 and 5. What is RB?
It's 4 and 2.
It is 4 and 2. What is delta R?
1 and -3.
RB minus RA, again, based on the understanding of the subtraction of two vectors, we said that we subtract their coordinates. So at the beginning, the x, 4 minus 3, then the y, 2 minus 5, right? So delta R is 1 minus 3. Let's verify what we got here. So the projection of my vector, the displacement vector on my coordinates is 1 minus 3. Is this correct? If you project delta R on the x, what are you going to get? Isn't that 1? Yes?
Yeah, it is.
If I project it on the y, what am I going to get?
2. That's 3, right?
-3.
Minus 3.
-3.
-3. So what I did is correct. So what I need to do now is I need to continue and find the magnitude and the direction. So in order for me to find the magnitude, then delta R here equals to the magnitude. What is the expression for the magnitude? The square root of the summation of their projection squared, which means 1 minus 3. So that's the magnitude. So delta R magnitude for this vector is indeed 3.2 meter. Somebody may say, how did you come up with this number? Why are you using the square root of and taking those projections and, you know, square them and add them? I would remind you with the trigonometry that says the following. If you extend this one, let me move this one a bit, extend this. Then isn't this delta R the hypotenuse of my triangle? Isn't this delta R Y and this delta R X?
It is.
Okay, so if I take the magnitude here, I can easily see that the magnitude squared equals to delta R X squared plus delta R Y squared. So what I did was not far from what you have learned in calculus. So this is the magnitude. So always the expression for the magnitude is the square root of the projection of the summation of the squared projection of the vector. This is always the case. Now, after I found the magnitude, I need to find the direction. How do I find the direction? It is enough for me to find the angle in order to define the direction of this vector. So if I am to give this theta, then what is theta in this case? It's tan inverse. Tan inverse of what? Can somebody tell me? Isn't it delta ry over delta rx? Is that right? Is that right? So theta is tan inverse of, what is delta ry?
The opposite over adjacent.
That's correct. The opposite over the adjacent, which is minus 3 divided by 1, which means that theta is minus 71.6 degrees. So why minus? I'll tell you why minus. Based on the understanding of the quadrants that we talked about, if I take this line, the horizontal line, which is parallel to the x-axis, I can treat it exactly the same way I'm treating the x-axis. So in this case, theta is minus 71. Why minus 71? Because I can see that the x component is positive and the y component is negative, which means it will fall in the fourth quadrant. That's why the angle is minus 71.6 degrees. Or if you don't want to look at it this way, you can say, or theta is 71.6 degrees south of east, which means this parallel line that is parallel to the x, I'm treating it as the direction of the east. And I can see that the vector is 71.6 degrees pointing south from the east. If this one is the east, then what you're seeing here is this vector delta r is pointing 71.6 degrees south from the east. Is that clear?
Yeah, that makes sense.
Okay. Now let's move on to B, average speed. What is the average speed? This is something we've done before. Average speed is the total distance, which is 18 divided by the total time, which is the 49, right? We said this is the total path length and this is the time. And in this case, the average speed was 18 divided by 49.37 meter per second. So this is B. Now let's move on to C. What is C? Find the average velocity. In order to find the average velocity, if you recall the average velocity, what is the average velocity? Can somebody tell me what is the average velocity?
Delta r over time.
Excellent. Delta r over delta t. Average velocity is the displacement divided by the total time. So in this case, if I am to find the average velocity, we said that we can find the magnitude first and then find the direction. So in this case, the average velocity magnitude is indeed the displacement magnitude divided by the total time, which is the 49. So let's find, or find the magnitude of the average velocity first. You remember how much was the average displacement?
3.2.
3.2 divided by 49. And in this case, the average magnitude of the average velocity is 0.065 meter per second. Now, keep in mind that the average velocity has the same direction as the displacement. Why? Because you're dividing the vector, which is the displacement here, by a positive scalar. And we have seen that dividing a vector by a positive scalar will only change the magnitude, will not change the direction, which means that the average velocity, what does that mean? Will have the same direction of the displacement, which is 71.6 degrees south of east, or minus 71.6 below the horizontal line. So that's it. This is how we solve for the displacement and the average velocity as well. Now, if we move to the instantaneous velocity, it's no different than what we have seen before. The tangential line at the point of interest, at the moment of interest, defines the velocity, right? So you can always look at the velocity as it has the magnitude, the instantaneous has the magnitude of the speed. However, the direction is different for the instantaneous speed. Let's look at this example to understand what I was just saying. If we have this path, as you can see, it's a path that is, going non-straight. The person is traveling at roughly constant speed. So the speed is constant. Which of the following vectors best represents the change in the person's velocity between A and B? So what I'm after is the change in the velocity, which means the change in the velocity means the velocity of the final destination minus the velocity of the initial. So in this case, I'm looking for VB minus VA. Is that right? So here we can do it this way. Let's draw the tangent line for the VB here. So this is VB. And the tangent line for VA. VA. Now, if you recall, when we said VB minus VA, we really meant, or we can also look at it as VB plus minus VA. For simplicity, we will reverse the one that we're subtracting and add it, because reversing a vector is very simple. You just change the direction, right? So the minus, remember what did we say about multiplying a vector with a negative scalar? It changes the magnitude and it flips the direction. So it makes it easier to me graphically to reverse the VA, and add it to VB. So in this case, I will reverse the VA and I will draw it this way. So this one is minus VA. And now I will add them. So I have here VB. This is VB. And then I will take VA. minus VA, I mean. Right, so this is minus VA. And which one do you think represent the correct answer?
A.
A. You are absolutely correct. So this is A. Okay. Now let's move on to this example. In this example, we have a merry-go-round horse travels at constant speed around the circle. We have this being rotating clockwise with a constant speed. It takes 20 seconds to complete one full turn. One full turn, one rounded trip, 20 seconds. The circumference of the circle is 31.4 meters. We need to find the horse's velocity at position A, the horse's velocity at position B. So let's start first by withdrawing the circle. And then putting the coordinates. I'll put the coordinates right in the center, like this. This is position A. This is position B. This is X. This is Y. Right? Those are my coordinates that I use them to do the calculation. Otherwise, how can I calculate it? So here, what I know is the circumference is 31.4. And I know the time is 20. So in this case, I can calculate the speed. The speed is 31.4 divided by 20. Then the speed is 1.57 meter per second. Okay. So this speed is constant. Now, if I am to look at the velocity, I have to include, remember what did we say about the difference between the speed and velocity? It's the direction of the motion. So I know that this is rotating clockwise. And I also know from the question that this up is north. So if I am at point A, that's the path, it's a circular path. In order for me to draw the velocity, I draw the tangent line. So the tangent line right here is perpendicular on the radius as well. So I can say that this is the direction of VA. So it is always perpendicular. If you have a circle, it's always perpendicular, and it's also tangential to the circle. So here I have VA pointing up. What about B? The tangential line at point B would be pointing toward east, right? So this one is V. This one is VB. Does this make sense? Tangential on the that circle, and pointing in the direction of the motion, which is clockwise. Now, in this case, I know VA at position A is 1.57 meter per second north. VB is 1.57 meter per second, and this is E. This is extremely important to know. How did we calculate the velocity right at those points? And based on the understanding of the direction of the velocity is in the motion direction, and at the same time tangential to the circle, or to the path of the displacement. Any question? No questions? Okay, so we found A and B. Now, what did we need to find? We want to find the average acceleration of the horse from A to B. The average acceleration. In order to find the average acceleration, I know that the acceleration average is also a vector. And this equals to delta V divided by delta T. What about delta T? How much is delta T? Can somebody tell me?
A quarter of 20 seconds, I think.
That's correct. It's a
5
quarter.
seconds.
5 seconds. It's 20 divided by 4 because this is a linear motion. The velocity is constant. The velocity is constant. So the ratio of the length of the elapsed distance is the same ratio of the elapsed time. So that's why I have a quarter of the circumference here. Then I have also a quarter of the time, and this equals to 5 seconds. That's correct. Again, in order for me to find the average acceleration, I will start first with finding delta V. Now, delta V equals to what? Equals to the velocity of the final destination, VB, minus the velocity of the initial point, right? Fine. So I have VA and I have VB. I need to find the projections of VA and VB, right? Didn't we say that whenever we're dealing with vectors, we will be dealing with its projections? So let's go and find out what are the projections in my case here. So VA is what? And VB is what? Can you help?
I think VA is going to be the radius of the circle, but a negative value for X.
VA, I'm talking about, well, this is not necessarily this. Don't look at the radius as the same length of the velocity, right? They're not.
Oh yeah, but if we're looking for coordinates.
Well, VA, my VA has two projections, X and Y.
Yes.
Focus on that vector.
Oh yeah, sure. Okay, for Y, it's going to be 1.57.
Excellent, 1.57. What about the X?
Negative 4.99.
Come on. When you project a perpendicular length on that axis, what is the projection? Isn't it a dot?
0.
Isn't it zero?
Zero. Now let's look at VB. What is the X for VB? What's the projection on the X-axis for VB?
Would it be 1.57?
What is the projection of the VB on the Y?
0?
0. That's correct. So now I found VA and VB. Now I need to apply what I have learned in terms of applying the mathematical operation on their projections. And I'll start with VB. So the X of VB minus the X of VA, the Y of VB minus the Y of VA, right? Delta V. Yes, go ahead.
So could you just quickly recap why it's 0? That's the only part that I don't get.
Why is it 0? Okay. So if this is my X and this is my Y, and I have here a length, a line that has a magnitude of, let's say, 5. If you project this line on the x, what do you get? Let's assume that this is my vector. It has a magnitude of 5. If you project it on the x, what do you get?
I don't know.
You get the same magnitude.
Oh, okay.
If you project it on the y, what do you get?
Oh, 0.
0.
Because it
has no component. It has no projection on the y. It is
That's because it's
perpendicular.
perpendicular. Okay, okay, thank you.
It's perpendicular on the y. And this is exactly what we have here. If you look at the VA, you will see that VA is perpendicular on the x-axis. And VB is perpendicular on the y-axis. That's why I have no component on the x for VA, and I have no component on the y for VB. So now back to my vector. So those are the projections now of my velocity change, right? So I will find the magnitude, because I will start first by calculating the magnitude of the average acceleration. So let me get first the magnitude of the velocity change. Then this one is 2.22 meter per second. This is the average, this is the magnitude of the velocity change. Now back to the acceleration, average acceleration that we had there. If I now look for the magnitude, then this is going to be magnitude divided by 5, which means that the magnitude for the average acceleration is 0.44 0.44 meter per second squared. All right. Now we need to find the direction for the average acceleration.
Sir, do you mind scrolling up a little?
Yeah. Now we need to find the direction for the average acceleration. How do we find the direction for the average acceleration? Remember, the average acceleration is the change in the
Thanks, I'm
velocity.
good now.
So it has the same direction as the change in the velocity. Just a second. Okay. So back to the equation here for my average acceleration. It has the same direction as the average, the change in the velocity. So if I take the change of the velocity direction, then here I have VB minus VA, and that's why I will flip the VA to minus VA. It will be easier for me to work on that. So this is minus VA, and then I will take it and I will put it here. This is minus VA, right? Then this is the delta V. This is the delta V. So for me, if I find this direction, I also found the direction of the acceleration. The average acceleration here, the average acceleration, right? So here, what do I have? The average acceleration is the same direction as the change in the velocity. So let's find the direction of the change of the velocity. I need theta. And theta here is tan inverse. Tan inverse of what? Tan inverse of VA over VB, which is minus 1.57 minus 1.57 divided by 1.57. And in this case, theta is minus 45 degrees, which is below the horizontal, or I can say theta is 45 degrees south, south of east. Okay. Remember, keep in mind that the average acceleration here and the change in velocity, they have the same direction. Why? Because delta t is a positive scalar. It's not going to affect the direction of the average acceleration. As simple as this. So this way, we calculated the average acceleration magnitude. I can now put the whole thing together and I can say that the average acceleration is 0.44 meter per second squared, 45 degrees south of east. Mission is accomplished. I found the average acceleration. Okay, so let's move on. Now, in case of the constant acceleration, as before, the average acceleration becomes the same as the instantaneous acceleration, and then this is going to lead us toward simplifying using this equation and deriving all the motion equations the same way we did in last lectures. But in this case, you get two, because it's 2D, you get the x and the y. Be careful here, you have acceleration in the x that is different than the acceleration in the y. You have initial velocity in the x, you have final velocity in the x, you have it for the y as well, right? So you have both in both domains. So keep in mind that you have two motions and two domains. Now, if I am to introduce the projectile motion, in the projectile motion, the difference is we don't have acceleration in the horizontally in the x-axis. We only have the acceleration of the gravity, and that's why in the projectile motion, ax is 0 and the velocity is constant. So the initial equals to the final. So in this case, all those equations and the x motion are simplified into this equation, the one that you know, x equals to vt. However, the acceleration is still there in the y motion because of the gravity. So keep in mind that in projectile motion, the acceleration in the x is 0, right? And here in this case, we only have acceleration in the down due to the gravity, and the maximum point you reach in the vertical direction has a velocity of 0. And keep in mind that the horizontal and vertical motions are independent, and we're dealing with ideal case where we have no air resistance. This is extremely important. So I will stop here